Let us continue our discussion about the step response. So, in the previous lecture, we were discussing about the step response of an LTI system, and we understood that the step response is denoted by S of t, and step response of a LTI system is the response of the system for unit step signal as input, and we know that unit step signal is denoted by U of t. So when your x of t, that is the input signal, is u of t, and h of t, which is the impulse response of the LTI system, so the convolution of the input signal, that is u of t and h of t, will give you s of t. So this is the step response of a system. So step signal is a very basic or a fundamental signal. After unit impulse signal, steps signal is the next fundamental signal. So how the system behaves when you give step signal as an input to a system. So a very important response we get, we get to know about the behavior of the system. So such response is called as the step response of the system, and this step response is denoted by s of t. Now if we use the convolution equation for computing the response s of t, then we can write the equation s of t is equal to minus infinity to, so this is t, this is not tau, this is t. So s of t is equal to minus infinity to t h of tau into u of t minus tau. Now if you see carefully here, this is our signal u of t. Okay, so this is t, so I can draw here, this is t, this is 0. Okay, so this is 1 if I can write, so this is my u of t. But now in convolution we know that we convert this u of t into what we call it as u of what, tau. Okay, so if we convert this u of t to u of tau, so instead of this t, it will be replaced by tau. Okay, so u of tau will be something like this. So this is your tau, this will be tau here, instead of t this is tau. Okay, and the same signal will be there. Okay, so 0, this is 0 and this is 1. Now in convolution we flip this signal. So this, if you want to make it u of minus tau, so this same, it will remain here same. So this is tau now, and now this is your minus tau. So this is 0, this is 1. So this is called as a time flipping. So this is u of minus tau. Okay, so this is u of minus tau, this is called as a time flipping. Now this u of minus tau, after this u of minus tau, then you, if you shift the signal, so the what will become, you shift was this signal by amount t. Okay, so if I shift the signal towards the right by an amount t, okay, so this is 0. Okay, so this my signal, so this signal is called as a u of t minus tau. So this signal is u of t minus tau. So what is the value of the signal u of t minus tau from 0 to t, or from minus infinity? So this is minus infinity. So if you see this value from minus infinity to t, its value is 1. Okay, so that's why from minus infinity to t, since the value of u of t minus tau is 1, we can write this equation as this is t. Okay, not tau. So this equation is s of t is equal to minus infinity to t h of tau. Okay, so this is true when the system is non-causal. What do you mean by non-causal? The system is non-causal means what? The system, his output is depending upon the present as well as future inputs. Okay, and how do we know that its output is depending upon the future input? Since the signal is present for negative values, so we know that a signal, when there is a causal signal, it is not present for negative values. We have seen this in the first unit. And when a signal is non-causal, it is present for negative values. Now since u of t minus tau is present for negative values, then we call this system as non-causal. So here we have the equation from minus infinity to t. So from minus infinity to t, this value u of t minus tau is 1. That's why we write this equation for the for this system, for this step response s of t. For this step response s of t is equal to what? Minus infinity to t h of tau d tau. But this equation again gets simplified when the system is causal. Okay, when the system becomes causal, so there is, the signal will be absent from minus infinity to 0, because causal signals are signals which are present only for positive values. So the signal will be 0 from minus infinity to 0. Okay, so this minus infinity to 0 part will go, and your integration will start from 0, other thing will remain same. So 0 to t. Okay, so 0 to t h of tau d tau is the equation for the step response of a LTI system. For which type of system? The system should be a causal. So you have to remember these two equations. What is the step response equation for non-causal system? What is the step response equation for causal system? So these are the two equations that you have to remember. Equation number 1, this is equation number 1, the first equation, and this is the second equation. Similarly, for discrete time system also, we have the equation of step response. So in this case, the step response is denoted by S of n. So I can write the equation for S of n is equal to k equal to minus infinity to n h of k. See here, the equation here is given correctly, because here it is not written k, because here if you see, here it was written tau. Okay, here it was written tau, so that tau is wrong actually. The counterpart of tau is k, but here the equation is written correctly. So here we are having the variable up to n. Okay, so S of n is equal to the range is from minus infinity to n h of k. Okay, now if you see, this equation will be for causal or non-causal. This will be for non-causal system. Okay, so this will be for non-causal system. Why non-causal system? Because negative values are there from k equal to minus infinity to 0. This will be, we are considering the negative values also, and when we are considering the negative values, the system is non-causal. And now if we modify this equation for causal system, what will be the case? Our system equation will be S of n is equal to k equal to 0 to n. So when this will be changed from 0 to n h of k, it will be for causal system. So these are the equations for step response in case of discrete time LTI system. For discrete time LTI system, we have to remember two equations. We can compute the step response of discrete time LTI systems by using the simplified equation. Now why this analysis is being done? In order to simplify this equation. That is, if you see these two equations, this equation and this equation, now you can see that these two equations are easy to solve compared to the convolution equations which we had seen. So when one of the input to LTI system is a step signal, then the equation of convolution gets simplified. So that simplified equation is being used for computing the convolution. So such systems, such response of the system for unit impulse signal, for unit step signal as an input, is called as the step response. So step response can be computed by using these equations, which are for continuous time and discrete time. Now we can have a simple numerical by using this equation. Suppose we want to compute the step response. We know the impulse response of the signal is given, h of n is given like this. So simply S of n, that is the step response, is the convolution of h of n, the given signal h of n, with u of n. From where u of n has come? Because I know that the step response of a signal system is nothing but the response of that system for unit step signal as an input. So by default, the another signal will be a unit step signal. So that's why I write here u of n. So when I substitute this h of n in this equation, so I'll get this. Now if I solve this further, if I open the bracket here, distributive property of convolution, I open the bracket. Now this is important. Now what will be the convolution of a shifted impulse with a unit step signal? Okay, so we have seen the time shifting property of convolution. So when we convolve a shifted signal with another signal, that signal gets shifted by the same amount. So at the output you will get u of n minus 2, and here you will get u of n minus 3. So this is your final output. Okay, so this is a simple numerical wherein we can compute the response of the. So here there is no need for solving for graphical method or like that. Okay, so simply by just noting down the